Hello everyone, I am Professor Walid Emar from Zarqa University and allow me please to take you on a brief tour of our research prototype. This research has a title of Analysis and Development of a Newly Optimized Quadrable Diode Boost Converter QDBBC integrated with an H-bridge enhancement filter tailored for electric vehicle applications. The authors of this research are Walid Emar from Zarqa University, Sama Faris from Isra University, Hassan Kanakir from Petra University, Fawzi Gharagir from Zarqa University, and Zaid Ziyad from Zarqa University. All these authors are from Jordan and work at Jordanian universities I mentioned earlier. Allow me, please, before we start the tour of the research prototype, to highlight the main outcome of this research. We see here the proposed converter prototype, which we are going to explain and to introduce to you. This study presents an advanced modification of the traditional quadratic boost converter, usually abbreviated as QBC. The new topology, referred to as the Quadrable Diode Boost Converter, as I have said, with an abbreviation of QDBBC, delivers a high voltage gain and demonstrates substational potential for various applications. These applications include power management and cyber physical systems, CBS, supporting modern secure operations, aircraft power systems, photovoltaic PV systems, and electric vehicle applications. So let's go now on the tour of the research prototype, please. Hello everyone, I am Professor Walid Emar from Zarqa University, from the Department of Energy Engineering, and I would like to introduce our latest research to you. Our study is focused on developing a new step-up boosting converter designed to achieve higher voltage gain, reduced current and voltage ripple, and also improved efficiency and dynamic performance of the so-called quadratic boost converter. We see here the circuit diagram of the traditional quadratic boost converter. Okay, we see here both circuits of the proposed converter, of our proposed converter, and of the traditional boost converter. We did a certain modification to this quadratic boost converter in order to generate, as I have said, a new converter that has higher voltage gain, better voltage and current ripple, better efficiency, better dynamic performance. Then the traditional quadratic boost converter, its circuit consists of a DC power supply, a DC voltage, in series with an inductive filter, simply an inductor. It has also three diodes, one main switch, MOSFET, IGBT, and so on, capacitive filter, another inductor, and it has a output diode D3, okay, capacitive filter, and the load we use in our experiment is purely a resistive load. We did the modification to this circuit in order to produce the proposed converter. We have added this H-bridge enhancement filter, as is shown here. It consists of capacitor, an additional capacitor C3, diode D3, inductor L3, and capacitor C2. This H-bridge enhancement filter is used mainly to reduce the ripple through the inductor currents, and also the ripple in the capacitor voltages. we can see throughout the paper that the ripple in the capacitor voltages is almost completely removed due to this H-bridge enhancement filter. We replace these two parts, these two components, this diode and the output capacitor of the traditional quadratic boost converter with a new boost converter. Okay, as we have here, that consists of inductor L4, MOSFET, another MOSFET, diode, output diode, and output capacitor, which is connected across the load. As I have said, in the experiment we use at this moment a purely resistive load. Let me now please go through the experimental prototype. We see here the 4 inductors of the main circuit of the proposed converter. We call the proposed converter a quadrable diode boost converter. Quadrable diode because it has 4 diodes. Again, as we see in the circuit, 4 diodes, D1, D2, D3, D4. It has also 4 inductors and 4 capacitors. The 4 diodes, they work in conjunction with the two main switches. Okay, so the 4 inductors we see here, L1, L2, L3, L4, all these inductors have the same value of 2.2 millihenries. On this implementation, we have 4 capacitors, we have 4 diodes, and we have 2 transistors. This is capacitor C1, we see here in the circuit, and the other one is capacitor C2, and this one that's connected to the ground also is capacitor C3. All these 3 capacitors have a value of 150 microfarads. At the output across the load, we have capacitor C, output CO, and it has a value of 470 microfarads. Okay? We have applied the delta modulation technique in order to adjust and control the current, the inductor currents. And for this target, we have 2 Arduino Unos that are programmed to produce a duty cycle, the same duty cycle for both transistors. I have to say that the proposed converter produces a higher voltage gain than the traditional quadratic boost converter. It produces a voltage gain which is the cube of the voltage gain of the traditional boost converter. The quadratic boost converter normally produces a voltage gain which is the square of the traditional boost converter, the very known traditional boost converter. But our proposed converter, if we apply the same duty cycle for both transistors, it produces a voltage gain at the output across the load, which has a cubic value of the traditional boost converter. As we see here, we are applying at this moment 6 volts at the input, and the supply current that flows from the DC source into the circuit is about 0.348 amperes, and the voltage across the output is about 8.60 volts. The waveform of the output voltage we see here on the scope, and the waveform of the current flowing to the load should have the same waveform, because as I have said, the load connected to the proposed converter is purely resistive load, which has a value of 100 ohms. So as we see, we did another modification. Increasing the duty cycle results in increasing the output voltage. As we see, the input voltage is still about 6 volts. The output voltage is now about 52.4 volts. Okay, at this moment it is enough, and we'll go now to see another video that's created via AI, where the working principle of this proposed converter is explained in detail. Thank you very much. Thank you for joining us, for being with us, and for joining this short journey about our research. Thank you very much. At the end, I would like, together with my colleagues from Zarqa University and the co-authors of this paper, extend our gratitude to the leadership and administration of Zarqa University for their exceptional support in completing this research within the labs of Zarqa University, and to thank them for their financial support that has been instrumental in the success of this study. And I would like also to thank all of you for joining us on this short journey and milestone. Thank you.